So our first speaker is Robin Geelen from KU Leuven, and the floor is yours.
Okay, hello everyone, and thank you, Damia, for the introduction. So my name is Robin, and today I will talk about a new FHE scheme that we designed to encrypt high-precision numbers, and which we call the Generalized BFV scheme. This presentation is joint work together with Frederik Verkouteren. So to start this presentation, I would first like to make a comparison between two FHE schemes that already exist. On the one hand, there is the BFV scheme, in which the goal is to do some computations over very small finite fields, which I will write as Fp to the d in this presentation. So P and D are small numbers. On the other hand, there is a scheme known as CLPX. In this scheme, we will do computations over some quotient ring of the integers, modulo some huge P. Another difference is that the BFV scheme allows us to pack multiple of these finite field elements into a ciphertext. Throughout the presentation, I will visualize this with these kind of hypercube structures. So in this toy example, we would be able to pack 8 finite field elements. Moreover, the BFV scheme allows us to do arbitrary computations that can be interpolated over a finite field via this so-called bootstrapping operation. In CLPX, no efficient bootstrapping is known. And then just to give you an idea of the size of the parameters that we are talking about, in the BFV scheme, we could work with a finite field of 2 to the 20 elements and pack 1,200 such elements in a ciphertext. In the CLPX scheme, we could work, for example, with this very large 2 to the 14-bit number as a modulus. But in practice, in some applications, you don't even need such big of a modulus. So for that reason, we will be asking the following research question. Can we think of a new FHE scheme that lies somewhere between BFV and CLPX? So a scheme that can do computations over some finite field of very large characteristic, that has the possibility of packing on top of this, and that can also do arbitrary computations via the bootstrapping. Before explaining our solution to this, I would like to motivate why these high-precision plaintext spaces are important to us. And I think I can be rather short here because there are at least 2 other contributed works in this conference which use high-precision arithmetic. The first one is an application in zero knowledge and will be the last talk of the day. In this application, they require arithmetic modulo this so-called Goldilocks prime, which is the 64-bit prime that you can see here on the slide. So it would be nice if this prime can be supported in our generalized BFV scheme. Another application is one in secure multi-party computation and is based on a concurrent work to our paper. In this application, they use arithmetic modulo even larger primes, up to 2,000 bits in size, which is simply impossible to support in regular BFV. A final reason why we would like to use these large primes is packing density. So remember that we would like to pack multiple elements in a ciphertext to increase parallelism. Due to certain mathematical reasons, this is only possible in a very efficient manner when using primes that are at least 16 bits in size. And for that reason, a very common choice is this Fermat prime that you can see on the slides. In terms of notations, I will be using the standard notations for cyclotomic polynomials, cyclotomic rings and fields in this presentation. So this phi m in particular is a cyclotomic polynomial. For a non-zero element of our ring that we write as t or explicitly as t of x, we will define the plaintext ring as the quotient ring modulo this t. So this is the ring that our data will live in. I will again explain our generalized BFV scheme by analogy to regular BFV and CLPX. Remember, in regular BFV, the idea is to compute over some small prime fields. The idea to do this is simply to take our plaintext modulus equal to p. So note that our plaintext modulus will be an integer. And then we encrypt under ring learning with errors, using some ciphertext modulus that is necessarily much greater than p. Now, CLPX circumvents the problem of having a ciphertext modulus that needs to be greater than p via a clever trick. So what they do is they take as the plaintext modulus not an integer, but a linear polynomial x minus b. Because of this, the shape of the plaintext ideal can be simplified. So since x minus b is in our ideal, we actually have that x is equal to b. So we can as well replace x with b everywhere. If we do that, this ideal on the left-hand side simplifies to this right-hand side, where we simply replace this cyclotomic polynomial by its own evaluation in B. Because of that, our plaintext ring will be isomorphic to the integers modulo this phi m of b, which we rename to p on the next line. Let me get back to this parameter example that I gave earlier, where we had for p this 2 to the 14-bit number. In this example, you can see that we indeed solved the BFV limitation, since we have a p which is greater than q, and this is simply impossible in regular BFV. We introduce our new generalized scheme, abbreviated to GBFV, as a unification that accommodates both BFV and CLPX. The encryption in our scheme is pretty similar, also based on ring learning with errors. In the slides, I will denote a ciphertext with these figures, where I write the message in the green region and the noise in yellow. And as common, decryption will then work correctly as long as the message and the noise do not overlap. One very important operation that we need in our GBFV scheme is a function to choose small representatives modulo t. This is what we call flatten. So flatten takes as input an element from the plaintext ring and outputs a representative of it with small coefficients. When we analyze the norm of flatten, we will see that it depends on two contributions. One of them is the cyclotomic ring that we compute in. This is the red factor. And the other one is the size of the plaintext modulus that we use. Let's make this a bit more concrete by considering a couple of examples. A first example is in the regular BFV scheme, where we use an integer for t. Here t is 5. In that case, flatten corresponds to a coefficient-wise reduction mod 5. In the case that t is a linear polynomial x minus 4, such as in the CLPX scheme, then flatten corresponds to a base 4 expansion, so we replace 4 with x everywhere. But flatten can also be defined for a more general modulus. In that case, the output of flattening will still be small, have small coefficients, but there is not really such an interpretation anymore. Let's now explain the goal of FHE, which is this computation on encrypted data, and I will do this via a case study of homomorphic multiplication. To do that, we first flatten our plaintext to get some alternative plaintext m hat, and then we multiply this plaintext by both parts of the ciphertext. As always in FHE, because of this operation, the noise of our ciphertext will get larger. And for correctness of decryption, it's quite important to have a tight bound on this multiplication noise. It turns out that this depends on two things. So one of them is the input noise, and the other one is the red and blue factor, which is the flattening bound from the previous slides. So from this inequality, you can see why it is important to work with plaintext moduli of small norm, since this will decrease the multiplication noise. Let us now study the structure of our GBFV plaintext space. To do that, we start from this general identity, which we always have for cyclotomic polynomials, and which is listed on the top of the slides. In contrast to CLPX, we take our plaintext modulus not as a linear, but as a nonlinear polynomial. And then we use a similar trick to simplify this plaintext ideal. So in this case, we will substitute x to the k with b everywhere. If we do that, you can see that we get native arithmetic modulo this integer here, which we again call p. And if p is a prime number, we will call it a cyclotomic prime, since it is obtained by evaluating this arc cyclotomic polynomial in an integer. I want to emphasize here that p is not necessarily a prime. It can also be a composite number. But for the rest of this presentation, we will assume that p is prime. Again, let us consider a couple of examples, in particular which primes fit into this cyclotomic shape. The first example is in the power of 2 case, so where we take m a power of 2. If we plug in these parameters, then we will get a prime which you may recognize. So this is the Fermat prime, often used in FHE to get optimal packing density. Another example is in the non-power of 2 case. For these parameters, we will get another prime that you may recognize. This is our Goldilocks prime, useful in the zero-knowledge application. So it's quite nice that both these primes can already be supported in GBFV. Now, more generally than just defining these individual parameter sets, we can also define parameter families that all use the same prime. To do that, observe what happens if we double k and if we square b. I mark the changes in red, and as you can see in the second box, we will get exactly the same prime numbers. To illustrate the concept of these parameter families a little bit more, I made this comparison table for the Fermat parameter family. So each of the columns in this table is one parameter set within the Fermat parameter family. In this leftmost column, you can see that we have a very small number of only 1,000 slots, but also the multiplication noise is rather low. In the rightmost column, which coincides with the regular BFV scheme, we have a large number of more than 16,000 slots, but also 25 bits of multiplication noise. So it's a trade-off between noise and number of slots. We could make a similar table for the Goldilocks prime as well. The conclusion would be the same. We also have this trade-off here. But note that the gain from using GBFV in the Goldilocks family is even larger, since this leftmost column has 7 times slower noise growth than the rightmost column. In the beginning of the presentation, I mentioned that our slots can be arranged in a hypercube structure. Let me explain this first for the BFV scheme. For the BFV scheme, we have an example of a 3 by 3 by 4 dimensional hypercube on the slide, and each of the subcubes here can be thought of as if it holds one finite field element. One crucial operation that we then need in BFV is permuting these slots. For example, mapping them up by one position in the vertical dimension. In the GBFV scheme, the situation is similar, except that we have a smaller number of slots. Because of that, only a subset of our slots will still be valid in the hypercube. Those are the slots that I colored in green. And the red slots cannot be used to pack any data anymore. Because of that, we need to be a little bit careful when implementing our rotations. So we must always map valid green slots to other valid green slots. We can never map a red slot to a green slot. That would correspond to an invalid operation. One important thing that we need in the SNARK application is adjoining roots of unity to define field extensions. In this slide, I just want to briefly mention that this is possible. For example, to define a quadratic extension, we simply need to multiply our index by an additional small prime factor of 7. Similarly, we can also define cubic extensions by multiplying by an additional factor of 3. The inverse operation of adjoining roots of unity would be eliminating roots of unity, and this is interesting if we want to implement our Goldilocks prime with power of 2 cyclotomics. Note that for this slide, I would like to thank one of the Eurocrypt reviewers who pointed out the possibility. To do this, the idea would be to start from a cyclotomic field with respect to a non-power of 2 index, and then take the relative norm from this extension field to the subfield, which is defined with a power of 2 index. Then it turns out that this alternative parameter set on the right generates exactly the same Goldilocks prime, but can be implemented with a more standard power of 2 cyclotomics. If I visualize this operation on the hypercube, then what would happen is that we would simply peel off one of the dimensions of our hypercube, and in this case go from a 3-dimensional hypercube to a 2-dimensional hypercube. Another operation that we can do in the regular BFV scheme, and which also extends to GBFV, is ring switching. Here the idea is to change the cyclotomic ring during the computation. I will not explain the mathematics of this, but on the hypercube, what would happen is that we would remove the top part of the hypercube, and as a result, also the number of slots in the Stoy example would reduce from 2 to 1. Another very interesting operation is converting a GBFV ciphertext to a regular BFV ciphertext. Now, before explaining this, I would like to emphasize that this is only possible under constant p. So you can never change the prime p that is used for the encoding. On the hypercube, what would happen is that we process a GBFV hypercube, where only 2 slots are valid in this case, to a fully defined BFV hypercube. And these slots that were green on the left will simply be copied to the right. The slots that were red on the left will simply contain garbage on the right. Now, the conversion routine from the previous slide doesn't really use the available BFV space efficiently, since there are many garbage slots. For that reason, we also propose a packing operation that converts multiple GBFV ciphertexts into one BFV ciphertext. To do this, we start from a set of GBFV hypercubes, where only a subset of the slots is green. Then one thing that we need to take into account is that we, for the second hypercube, need to rotate each slot one position to the left so that they do not interfere with the slots from the previous hypercube. Then we run the conversion routine from the previous slide and add everything up, and this forms one nicely packed BFV hypercube. For our GBFV scheme, we also introduce a bootstrapping operation. Now, due to certain technical limitations, we were not able to instantiate all of the bootstrapping steps directly in GBFV. Therefore, we also need to rely on this conversion to the regular BFV scheme. And as you can see in this slide, some of the steps will be evaluated in the BFV domain, while the last step, the digit removal, is executed in GBFV. Similarly, we also propose a batch bootstrapping to increase the throughput. Here the idea is that we would replace the conversion routines with packing and unpacking routines. We implemented this new bootstrapping on top of the Microsoft CL library, and this table shows some experimental results for single bootstrapping in combination with the Fermat prime. A notable difference with previous works on BFV bootstrapping is that we can instantiate our scheme with smaller parameters due to the reduced noise growth of GBFV. Because of that, we have a rather small bootstrapping latency. So as you can see in the bottom line, we have only bootstrapping latency of 2 seconds in total, which is roughly 5 times faster than regular BFV bootstrapping. Okay, so to conclude in this presentation, I described our solution for better FHE to instantiate it with these large cyclotomic prime fields. This has a very flexible trade-off where you can choose the number of slots that you want, and based on that, you get either faster or slower noise growth. And then we have a quite fast bootstrapping operation, which results from the smaller parameters that we can use in our FHE scheme. And one limitation that we have in the bootstrapping is that we need to convert to this, to the regular BFV scheme, since we do not know how to instantiate all of the steps directly into GBFV. Okay, thank you for listening.
Are there questions from the audience?
You said that we can't map a green slot to a red slot, but you do it before switching from GBFV to 1BFV. So what makes the difference between these two cases?
Sorry, I'm not sure if I understand the question. Is this about the question about the bootstrapping operation?
No, you said that when we do a rotation of slot, we can't map a green slot to a red slot.
Yes, I remember.
But this is something that you do when you switch from many GBFV ciphertext to one BFV ciphertext.
Yeah, in this case, this is allowed because the output will be a BFV ciphertext, so we need to use this additional space, these red slots, which are not available in the GBFV ciphertext. When we convert to regular BFV, we can use them, but then you need to change some things in the encoding, which I couldn't really explain in the presentation. But it's only possible in the conversion routine. When you're just computing in GBFV itself, we can never map a green to a red slot. Yeah.
Thank you.
Any other question?
Yes, so thank you for the very interesting talk. So you mentioned that for doing the PBS, you need to, for some steps, you need to convert to the regular BFV scheme. Do you have a feel for the performance implication of this?
The difference in performance is that there will be, during these steps, there will be more noise growth because the BFV scheme has more noise growth than GBFV. In terms of efficiency, it's rather similar, I would say. But there will be more noise growth in these BFV steps.
Yeah, thanks.
I also have questions.
Okay.
I'm always very impressed by bootstrapping implementations. So congrats. Can you go back on the slides on the performance of bootstrapping? So I was wondering whether you could give more details, like, you're not on this.
Yeah.
I can continue my question while the slide comes. So security level, number of threads, is it single thread CPU? Is it 128-bit security? How many levels do you have left? Is the code available?
Yeah, the code is available. It's 128-bit security and it's single core. And then in terms of levels left, Yeah, one line that I didn't discuss, for example, in this table is this remaining noise capacity. So it really depends on which parameter set you use in the GBFV scheme. If you use a parameter set with a small number of slots, then we will have more levels left because there is less noise blow up during the bootstrap. If we use a parameter set with a larger number of slots, this right-hand parameter set, then we have smaller remaining capacity, yeah, because there's more noise blow up during the bootstrapping. Thank you.